Great, so welcome to the plane curves class today. In the last lecture, we introduced the intersection multiplicity of two curves, or polynomials, and let me quickly just recall what the definition was and what the basic properties were, because the first thing today is that we want to see how we can actually compute that. So in that sense, that touches like a little bit like a lecture of computer algebra. The question, we defined now some algebraic object, but how do we actually compute it? So the setup was to say if we have, I think we need three curves or polynomials, meaning so always in two variables. Then first of all, we had defined for a point P in the affine plane a so-called intersection multiplicity, which was denoted mu P, then of F comma G, which was defined by, you take this what we call the local ring OP of the plane at the point P, you mod out the ideal generated by the two polynomials or curves, and then take the dimension as a k-vector space of that thing. So that was the definition, and we saw a couple of properties of that. So quickly reviewing that, as I said. So first of all, we saw that any operation, of course, on the polynomial that doesn't change the ideal will leave this thing invariant. So if we have mu p of f and then g plus the first thing times another polynomial, then that will be the same thing as mu p f g, just because simply the ideals are the same generated by the two. We saw that if in the origin, so one example computation, basically the only one we did so far, was that if we take the curves x and y, so the two axes, and consider that in the 0 point in the origin, then the multiplicity is 1. Actually, we had seen in general that this is sort of translation invariant in the sense that it suffices to consider the origin. If there's any other point we're interested in, we can just shift the coordinates to the origin and then compute it there. We saw a criterion when this multiplicity is non-zero, namely mu p of fg is non-zero, so greater than 0 if and only if the point actually lies on the two curves. So if p is an f intersect g. We also saw when it's finite, then the mu p of fg is finite. If and only if there is no common component of the two curves at the point p. So f and g have no common component through p. And the last thing, there was the proposition that we proved at the end of last lecture, was the additivity statement, namely if we take mu p of f and then a product, so g times h, then this is always the same as mu p of fg plus mu p of fh. That followed from an exact sequence that we introduced last time. So these are the properties that we know so far of this intersection multiplicity. And as I say, so the question is now how to compute this. And so if you're interested in questions like that, then you probably want to go to some computer algebra classes or whatever. So in case of this intersection multiplicity, let's start with one simple example. And that will lead then to the general algorithm later on, like in the next point here. Namely, let's first consider the motivating example even that we had at the beginning, namely where we take one curve and intersect it with the horizontal axis. So take intersections. So with the horizontal axis, what would be y as an equation? So that means we have this is y, and then any other curve essentially, like this would be f, and a point would be the origin. Is 0. Before. So let's say we have such a curve f, so let f be a curve, well, let's consider the finite case where we don't have a common component, so that means that doesn't have this y as a component. Otherwise, the result would be infinite anyway. Component. And we want to compute mu p at the origin, so mu0 of y and f. And the intuition was that this should be the order of the zero of this graph of a function if it's the graph of a function, and otherwise it has a similar geometric picture. And we can actually see this quite easily that this is exactly what happens, because the first thing we could do if we compute that is we could use here the first property to just remove any occurrences of y in f. Right? So if f contains any term with y, we can just subtract it because of the first entry. That's just the first property. Maybe let's just give them numbers so I can refer to them. So 1, 3, 4, 1 up to 5. So by 1, we can replace f by f of x of the polynomial where we put 0 for y. So let me write it like that. Or fx comma 0. Just we subtract all terms with y. And so that means that's a polynomial in x only. So we're in the simple case where we have like the simple polynomial y and one polynomial that depends only on x. And that, of course, we can write as usual as a polynomial. And I want to factor out the lowest occurring exponent of x. So I write this as x to the m times g, where g doesn't vanish at 0. i.e. the m is the lowest exponent of x. And that would be, of course, if we consider that as a function, and x would be the order of the origin as in the standard definition, right? Of the origin at this point. So, and we will get the result m here as well, because then we can just compute this. So we have mu0 at y comma f is then mu0 by this computation here of y and x to the m times g. Because we could replace it by that one. And then we use this last multiplicativity, right? Just to split off the last product. So by property 5 up there, we could write this as m times mu0 yx plus mu0 yg. But this one here is 1. That was the computation up here, which we call 2. And the last one would be 0 because g doesn't vanish at the origin. And that's just property 3. So that means this here is 1 by property 2. And this is 0 by property 3. And so the result is just m, and that's, as I said, what we would expect it to be. Then it's just the order of the 0 if we consider that f of x comma 0 as a function in x. So that's a very first simple example where we have one of the curves being equal to y. Now what we can derive from that is a general algorithm. So that means if we have any two curves with no common components, say at the origin, algorithm, so the computation of mu, so let's again do it at the origin, so mu0 fg, otherwise we just shift to it. So we let f and g be two curves or polynomials, doesn't matter, that do not have a common component through 0. Then to compute the intersection multiplicity, we do the following thing. So it's a recursive algorithm. So to compute mu0 f comma g, so we perform recursively the following steps. So the first thing is we just check for the trivial case if this might be 0. So if one of the curves doesn't pass through the origin, then we would get 0 by 3, and then we just stop, of course. So if f of 0 is not 0 or g of 0 is not 0, we obtain that UP of Fg is 0. So that was the property 3 up there. And so then we can just stop the algorithm. So this is where it will stop eventually. So let's assume this is not the case. So they both pass through the origin. Then we still have to distinguish two cases. And the first one is that both of the polynomials, both of the curves f and g, contain a monomial that has only x and not y. So it's the case B. So both f and g contain a monomial that depends only on x and not on y. And then the case C will be that this is not the case. Right? So that's the first case, first non-trivial case. Then we'll just separate this term. So we'll write f is from, say, a times x to the m, where this should be the highest occurring pure x power. And then the remaining terms are just anything we don't care about. So there's more terms that either include y, so let me just write terms with y, or that do not contain y but have a lower power of x. And then we do the same with g, right? And so we assume that both of these terms exist and are non-zero, so that means a and b are non-zero numbers. So we have bx to the n plus, again, terms with y or with lower power of x. So that's the form that we assume here in case B. And what we do then is essentially a Euclidean algorithm thing, as we would compute the GCT, if the GCD, the greatest common divisor, if there was only one variable at all. So that means we assume, say, that m is the larger number of the two, or at least greater than or equal to say, without loss of generality, m greater or equal to n. And so what we do is just we take a multiple of g and subtract it from f so that this term is cancelled. Right? So that's what we do, and we just don't care about the rest here. So then so what would it be? So we call it f prime. We'll say it's just a new polynomial, not derivative or anything. So it's f prime should be f minus, and then we take something times g, and we want to be that the same as that, so it means we have to multiply it with x to the m minus n, and then the product a over b. So in this difference, then this term will just cancel that one, and that means this new polynomial here has the property that it has a lower exponent of x, but otherwise has the same thing. So basically, the other properties remain. So also the f prime will pass through 0 because f is 0 at 0 and g is 0 at 0. So this will again be 0 at 0. So that's still true. And we have made a transformation as what we call the one up there. Oh, I just erased it. So the first thing that we could take an ideal and just add one multiple of one polynomial to the other. So that means if we replace f and g by f prime and g prime, that will not change the intersection multiplicity. So we know that mu 0, but f prime g is the same as mu 0 of f and g, so we don't change this number by what we call 1 up there. And that still passes through 0 because f and g do. And we've lowered the number, so say m plus n, right? So we haven't replaced n, but we've made n lower. So m is strictly decreased. And so this means if we repeat this step a couple of times, we will eventually run into the case where one of the polynomials doesn't contain a monomial like that anymore, right? So this have to, we just repeat the step, and after finitely many times, as we have a natural number that's strictly decreased, that must end at some point. So we perform the step. Recursively. We'll say repeat the step. And after finitely many iterations, it has to stop, as this natural number is always decreased. So as m plus n is strictly decreasing, and this leading then to the last case. So, and that's case C, where this is not the case. So this means where one of the polynomial has every term with a y, so it doesn't contain a monomial that depends only on x, and that's the last case. So f or g, by symmetry, just we say it's f, contains only monomials with y, containing y. And so we finally have to run into that case. Just say, so just remind you, like this b is just the same way as you would just compute the GCD of polynomials in one variable. You just take all these terms with you, but you don't really care about them. So we'll see an example in a minute. So if, say, f contains only monomials containing y, this actually means that y is a factor, right? So this means f would be y times f prime, or some f prime. And then we can use our additivity. So that means the mu 0 of f and g would be mu 0 of y f prime and g. And then we can split this up into a sum of two terms. That. So there was the property 5 up there, which means mu 0 of fg will be mu 0 of y comma g plus mu 0 of f prime comma g. And the first one is actually a case of this example that we considered before, right? Where one of the curves is y, and so we could just compute it by replacing y by 0 in g and then see what's the lowest monomial in x that occurs. So we can this just compute by the example. It's just the lowest exponent of x in g of x comma 0. As the curve passes through 0, so we just assumed that there will be a positive number. So that means this is strictly greater than 0. And so that means this number here is actually strictly smaller than that one, mu 0 of f comma g. And it's finite, because we assumed that there would be no common component. And that means if we now continue recursively, so we use the same algorithm again to compute this intersection number, then again we will eventually stop because we have a finite number and it's decreased every time. So repeat the algorithm recursively to compute now the last term from mu 0 of f prime comma g. So this will stop since this number mu 0 of fg, which is a natural number, so it's finite. So the point is it's finite by, I think it was 4 or something we called before. It's strictly decreased every step. And so that means that algorithm will eventually compute you this number. Let's just do that in one simple example. And I think you see how this works. And the example that I took in the, I think in the notes was here. You want to consider f is the curve y squared minus x cubed, and g is the curve x squared minus y cubed. So if you draw this, then we had this on the board once. So y squared x cubed in the real picture would look like this. That would be f. But essentially, it's y is x to the power of 3 over 2. And x has to be positive because that's always positive. So we're on the right half of the thing. So that would be f. And g is the same thing with x and y reversed. So that would look like this. So that's two curves that do some weird thing here at the origin, and we want to compute its intersection multiplicity. So then we can just use the algorithm. So mu0 of f and g. Copy this. So it's mu0 of y squared minus x cubed and x squared minus y cubed. Then actually we are not in case A because both curves pass through the origin. So we are in case B because f and g, they both conterm a pure x term, right? So there's a pure x term here and there's a pure x term here. And this is the higher one. So we'll use the algorithm B up there where this is f and this is g. And subtract a multiple of the second polynomial from the first so that this x cubed cancels. So this means we copy this one here. And obviously we have to multiply this by x. So we add x times the second polynomial. Like that. And we copy the second one. So that's the algorithm part B. So, And the reason why we do is because the x cubed cancels. So now we get mu0 of y squared minus x cubed plus x cubed. And then we have a minus x y cubed, I guess. And the last one is still there. So now we're in case C, right? Because we've already finished, because the first polynomial doesn't contain any monomial anywhere without y. They all have y's in there, so that means we can factor out y. So we can write it as mu0 y times y minus xy squared, and then x squared minus y cubed, and use the additivity. So that was just what we call C in the algorithm. So we'll get mu0 of y x squared minus y cubed plus mu0 of y minus xy squared. X squared minus y cubed. And that's the case of the example. So one of them is y. That means this multiplicity here by our example is set y equals to 0 here and see what the lowest power of x is. That's 2. So this is 2 by example. And then we continue recursively to compute this intersection multiplicity. And actually, in that case, we're again in the case C, where the first polynomial contains only terms with y. So we can factor y once again. And obviously, we could have factored y squared already here, but just want to follow the algorithm strictly as it stands. So we're again in case C, can factor out a y. Again, get the same term as before, so another contribution of 2. So this, we copy this 2. And then again by C, another term of this form. So mu0 y squared minus y cubed plus the thing here without the y. So mu0 of 1 minus xy x squared minus y cubed. So this is again 2 as above. And here we are already stopping the algorithm because that's the curve that doesn't pass anymore through the origin, right? So 1 minus xy is non-zero at 0. So that means this is 0, and that will be part A, like of the algorithm. And so we stop eventually, and we get 2 plus 2, which is 4. And so that would be an example computation of that thing. And you could do that for any curves that, at least they don't have a common component to the origin. Maybe one remark what happens if it does have a common component through the origin. So well, actually the computations that we did in the algorithm are not false in the case when there is a common component. So we just used the general properties of intersection multiplicities that we had shown in any case. But it might actually not terminate. So it might or might not terminate. So here it has to, because we are starting with a finite number, reducing it every single time. But if we have an infinite intersection multiplicity, we might reduce a finite amount every time and never stop. So just a remark. So if f and g do have a common component, through 0, so that the intersection multiplicity is infinite, so mu 0 of fg is infinite. Then the algorithm might, so it's still correct. So we don't use any equations that would be false in this case, but it might not terminate. And so here will be an example where this happens, and it's quite easy to find one. I think it was, what was it? Just have to copy that here. So it was x squared and xy minus x. So again, try to compute mu0 of x squared xy minus x. So these two curves obviously have the common component x. So x is a factor of both of them. And x also passes through the origin. So if we don't care about this and just start the algorithm, then we would say, well, let's just check whether there is a term that is a pure x term. And so we have one here, and we have one here. So we have to add a multiple of this to cancel that. So that means we take mu0 and then x squared, just take again x times that thing, plus x would be part b of the algorithm. Xy minus x. The polynomial remains, xy minus x. So what we obtain is here x squared minus x squared. So we just have x squared y. Nothing else. And xy minus x. Now we have y as a factor. Every term has y as a factor. There's only one term. So that will be by part C of the algorithm mu0 of y and xy minus x plus mu0 of x squared and xy minus x. And this is actually, again, set y to 0, take the lowest exponent. This would be 1. Our example, and this is just the same as before. So that means you would run into a loop. In our algorithm, and it would never stop. Actually, the equation as it stands there is still correct. It just says infinity is 1 plus infinity. So it's not false, but it doesn't help. And so that's what could happen. But as it is true in any case, the remark is just that if you just try the computation and it does stop with a finite result, then you know it's true, and in particular, you've then also proven that there is no common component through the point. And that's what one probably would usually do. So just start the computation, and if you're lucky, it will stop. And then you also know it doesn't have a common component. So you don't really have to check this assumption at the beginning. It will be proven then by the algorithm. But if for any given curve the algorithm terminates with a finite answer, then this also proves that there is no common component. Component through the 0 point. So and that's what one would usually do. So the assumption in the algorithm where it says at the beginning, let's assume f and g are curves without a common factor through the origin, you would just ignore that, usually just go ahead and compute. And if the algorithm stops, you've proven it afterwards. Right, so that will be one example, probably the last one in the whole class here, just to see like one example of what computer algebra could do. Right? So it's just a question after having defined an algebraic object as this intersection multiplicity, which is a bit hard to grasp maybe at first, just to not just prove the theoretical properties, but also you want to be able to actually compute and for any two given curves. Right. Then I think we know quite a lot about intersection multiplicity already. So any questions about it? So now let's look at one special case in more detail, namely at the most important case, the most important non-trivial case. Of course, there's the trivial cases where you have 0 or infinity, because the point doesn't even lie on the curve or there's a common component. So the most important case otherwise would of course be where this multiplicity is 1. And we had one case already like of the two coordinate axes intersecting with multiplicity 1. But we want to study that in more detail when this is actually the case. So the question is, so when is the intersection multiplicity equal to 1? Because that also has a nice geometric interpretation then afterwards. And for that we need one notation. And then we can prove a proposition about that right away. Namely, for a polynomial in two variables, as we usually consider it here, or a curve, we just separate the components of the various degrees. So for f, a curve or polynomial in axy, we denote by fi the sum of the terms of degree I so such that our f is then f0 plus f1 plus and so on plus fd, where d is the degree of f. And each fi would be homogeneous of degree I. So we just separate the homogeneous parts. I.e. fi is homogeneous of degree I. And we would then call f0 obviously the constant term, f1 is the linear term, f2 is the quadratic term. And then there's several terms in general. So that means the linear term, for example, could contain it's a constant times x plus a constant times y. That will be generated by x squared, x, y, and y. And so on. Yeah, now we use actually in the proposition, which can tell you quite concretely when the intersection multiplicity is 1. Namely, let's assume we have two curves. About intersection multiplicity 1. So for that, we say let f and g be two curves, say through 0. And then the intersection multiplicity is 1. Mu 0 at the origin. fg is equal to 1. So you know it's always, if they are through 0, I mean it's always greater or equal to 1. And it's exactly 1 if and only if the linear parts of f and g, so that's what we called here f1 and g1, if they are linearly independent. f1 and g1 are linearly independent. So recall, I mean, these will be linear polynomials in x and y, so they live in a two-dimensional vector space, in the vector space of homogeneous linear polynomials in x and y, ax plus by. And we have two elements, and if they are linearly independent there, so in other words, they form a basis of that, then exactly then the multiplicity, intersection multiplicity is 1. And we can see what this means geometrically afterwards, but let's first just prove that, because that is, again, a proof that uses the algorithm. So we'll just follow the algorithm with general curves like that and see what happens. And then the algorithm will actually tell us exactly this result. Right? I mean, it can compute the intersection multiplicity in any case. Or we can apply it here, we just need to apply it to general curves. So the proof will be as follows. So yeah, the same. Let's follow the algorithm. With f and g. And there were 3 steps, recall, right? So A was if the curves don't even pass through the origin, then we stop with 0. But that's not happening because we're assuming they pass through 0. So A doesn't happen. Right? Because we've assumed that f and g both pass through the origin fraction. So let's have a look at step B. In B, we performed these steps where we subtracted like a multiple of g from f. I'll just write this down. So we'll consider the step which was f prime was, it was of this form, f minus a over b times x to the m minus n with the notation step we had up there. Notation is just from above. It doesn't really matter anymore what this is. And actually f and g, as they pass through 0, the constant terms here would just be 0. So that means f0 and g0 are 0. Because they pass through 0. So what happens, and the only thing I want to look at, and that's the only thing we need at the moment, is what happens to the linear terms. So, of course, g is not changed at all by this step. So what happens with that? What's the linear term f1 prime as compared to f1? Well, that depends on the power of x here. So g doesn't have a constant term. So that means if m is actually greater than n, so that means there is at least one x and there's at least one variable in each term here, then this will have no linear term at all. So the second part is just has 0 linear term, and we just get f1 prime is equal to f1 if m is greater than n, right? Because then, so g contains no constant term, and then x, the m minus 1, are also no constant term, x to the m minus n. So, and that means the degree of this thing of a over b g x to the m minus n is at least 2 of every term. So, yeah. Wow. In a over b g x to the m minus n is at least 2, so it doesn't have a linear one, and it's just the same. If not, if m is equal to n, so then this is gone, then we just take the linear part here, right? So that means then f1 prime is f1 minus a over b g1. So f1 prime is f1 minus a over b g1 otherwise. In any case, this doesn't change the property whether f1 and g1 are linearly dependent, right? Because, or independent. Because here, of course, we don't change the linear part at all. And here we just make a standard transformation, like passing from f1 g1 to f1 minus this times g1 and g1. And these, so this and g1 is, this family is linearly independent if and only if f1 g1 is linearly independent. So that means whatever we do in step B, it will not change this property at the end. And it also doesn't change the intersection multiplicity. That means whatever we do in step B neither changes this side nor that side. So we can just ignore this altogether and pass right away to step C. So in any case, passing from f and g to f prime g prime doesn't change. First of all, it doesn't change the multiplicity, mu 0, and doesn't change if f1 and g1 are linearly dependent. And this means we can essentially ignore part B of the algorithm because it will not change anything. So let's pass to C. So C was that we can write f as y times f prime. And then was mu 0 of f and g was mu 0 of y g plus mu 0 of f prime g. And we actually stop right here because we want to check if this is 1 or not. And we know that this number here was always greater than 0 because g passes through the origin and this as well. So this is always greater than 0. And so this means this is 1. Of course, if and only if this is 1 and this is 0. And if this is 0, we also stop, right? So that means we're already at the end of the algorithm. So this is the case if and only if mu 0 yg is 1 and mu 0 prime g is 0. That's the only way how we can get 1 if the first number is positive. Now that this is 1 means by our example in the algorithm that when you replace y with 0, then this g contains an x term, right? So there is a term x in g. That means g1 contains the term x to the 1 and y to the 0 then, of course. Or g contains that, but it will also be in g1. And the second here means that this is 0 means that f prime doesn't pass through 0 anymore. So that means f prime contains a constant term. Oh, we could maybe write here g. And f prime contains a constant term. And for the linear part now, so that means we can write g as g1 as for some ax plus by, and it does contain a term x to the 1 y to the 0. So this a is non-zero. So we don't know about b, but a is non-zero. And if f prime contains a constant term, which is non-zero, then f, which is just y times that, means that f1 is just y times this constant term. So that means f1 prime is just c times y, where c is non-zero. Right? So this c is this constant term up there. And these two ones are obviously linearly independent. Right? So that number is non-zero. So y occurs, and that number is non-zero. So that means they are linearly independent. Let's first write it down this way. So from that, it follows that f1 and g1 are linearly independent. But actually, the other way around works as well, because we always have in this case that f1 prime cannot contain an x term, because, well, no, it's f1, not f1 prime. f1 cannot contain an x term because f is y times something. So the x term of f1 is always 0. And if we have anything like that with ax plus by and c times y here with no x term, then if they are linearly independent, we must have this number to be non-zero and this number to be non-zero. So that means we also can go back here. And then we have a sequence of equivalences here, and that would be the same. So that's one way to prove it, for example. It's just following the algorithm and see that. So we get just not with concrete polynomials, but with general ones, and check when we get one. So what's the picture here geometrically? I guess it's sort of clear, I guess. Namely, if the constant term is 0, so we have curves passing through the origin, then the linear part could somehow be considered the linear approximation to the polynomial around the 0 point. Right? So it will give you an equation of a line, which we could consider as the tangent to the curve. We'll just define that in a minute. And the condition then just says that both of them really have a tangent, so they have a linear approximation, and they are different. Right? So geometrically, we can say that f1 and g1, if they are non-zero, are linear approximations of f and g at 0, i.e. the tangents. So this mu0 of f and g is 1 if and only if these tangents are not the same. Let's draw a picture. So if we have the 0 point here and we have one curve, this would be f, and another curve which is g, like that, then the linear approximations to f1 and g1, they would look like that. So as a curve, this would be f1. As a curve, this would be g1. The linear approximation at the point, the origin. And linearly independent, of course, just means, they are not the same line. They don't define the same line. And then we have an intersection multiplicity of 1. So that's the intuition behind that. And we want to actually define this, and define this also in the cases when these terms may be 0, so the linear terms. Then, so if there's no linear, if the linear approximation is trivial, it's 0, then in general we would say like that the lowest terms, right, would be the best approximations. So in general, of course, the reasoning is that if x and y are small, then linear terms are larger, or like the other way around, then quadratic terms are smaller than linear ones, and cubic terms are smaller than quadratic ones. And so that means the first actually occurring term would be the relevant one for the approximation. So in general, the lowest degree terms in f and g can be considered as the best approximation around 0. And that we actually want to define as a constant. So for a polynomial f or g, f and g, or take just one f1 polynomial only, for a polynomial f, through the origin, or not. What is most important for this purposes here, to study the local behavior around the 0 point, would actually be the lowest terms that occur in F. And that we would also want to call a multiplicity, namely the multiplicity of the origin in this polynomial. So that's the definition where we talk about multiplicities of now polynomials, so of curves at a point, and then also leading to tangents. And we let the F be a curve. Then, first of all, we say that we define this first of all for the origin, because there it's valid. I mean that the lowest degree terms are the best approximation at the origin. The lowest, I'll say the multiplicity M0 of F, so that will be the notation for that, of F at 0 is the degree M. That is the smallest number, M, smallest natural number, such that the degree M part is non-zero. So it's the degree of the first, like in the sense of lowest term occurring in F. So this Fm is then a homogeneous polynomial in two variables, and we have a unique factorization domain that factors, and you might get linear factors from that, and any linear factor of that will be called a tangent of F at 0. Any linear factor of Fm, it will necessarily be a homogeneous one, because that Fm is homogeneous, is called the tangent to F at 0. That's at the origin, and we'll just consider examples in a minute. And if we're not at the origin, we just make a coordinate shift as usual, as we did with the multiplicities. So for a general point, P, say with coordinates x0, y0, we just shift coordinates first to the origin and then apply the definition A. So that's probably the easiest way to get this number, and that would also be the way to compute it. So for a general point like this, shift coordinates to x prime, which would be x minus x0, and y prime is y minus y0, and apply the definition A above to the origin in the prime coordinates to obtain both the multiplicity, which we'll call then MP of F, and tangents of P of F at P. So we'll see examples of all that in a minute. But first of all, maybe, so let's say one more thing in this definition. So we said this number M could be any natural number, in fact. So if we pass to the point, it will be non-zero, but it might not be 1. But if it is 1, so in the case that there is a linear term, F1, then of course, there is a unique linear factor here, which is just F1. And so then there is a unique tangent at the point, and hence we could give this a name, and we would call this just TPF, so T for tangent, and then the point and the curve. So the sum of those two possibilities that are of interest are, so note, first of all, MP of f is 0, of course, if and only if p is not even on the point, on the curve. P is not equal to f. And we see this here at the 0 point, so that there is a constant term is exactly saying that the curve doesn't pass through 0. Here we just shift it to the origin. And if the multiplicity is 1, then of course there's always a unique tangent because f1 itself is a linear polynomial. Of f at p, and this we will denote t and then p f. Otherwise, there might be more than one tangent, and so as I say, we'll just have examples of that in a minute. But let's just first consider this case of multiplicity 1 in again more detail, because the multiplicity 1 case is the the nicest one, the most interesting one. So there's some special definitions for the case for multiplicity 1, namely, then we can just apply all this in examples afterwards. Namely, this is about smooth and singular points and curves. And for that, again, let f be a curve and p a point in A2. Then, and it should actually be on the curve, so p and f. Then we say that p is a smooth point if this multiplicity is 1. That's the definition for us here. There's several equivalent ways to define that, but that would be 1. So P is called a smooth point, or some people also say a regular point of f if this multiplicity is equal to 1. Otherwise, if it's not, it's called a singular point. Or some people also say it's the singularity of f. And B, as one might expect, so we call the whole curve smooth or regular if every point is smooth or regular. For f is called smooth or regular if f is smooth at all points, and otherwise it's called singular. Yeah, so let's consider some examples, I guess, so that we can see that we can try out all these definitions. So let's draw pictures and check all the various properties. So maybe let's start with a very simple one. So y minus x squared would be like the standard parabola. If we consider the real picture, it looks like this. And we're always considering the origin here because there it's easy to read off all these properties. Then, so if that is f, then of course the lowest occurring degree in this polynomial is 1, namely y is a linear term. There's a linear term. So that means f1 here is y, and which is non-zero. And so this means the multiplicity at the point 0 of this curve is 1. So that means we would call this a smooth point. Multiplicity is 1. And hence this is a linear polynomial, and that is a unique tangent, and we call this the tangent to the curve. And y is just this thing here. It's the linear approximation. So that means dp f is y is the unique tangent. So that would be a first example. So next example would be f is this curve y squared minus x squared minus x cubed. So this looks as follows. If you draw this, we also had this on the board in the very first example sections. If you draw it, it looks like that. And we can actually see some of the properties already. So what happens here? So the lowest occurring terms are quadratic in this equation, right? So y squared and x squared. So that's the lowest terms. So here we consider f2, which is x squared minus y squared. Oh, y squared minus x squared, the way around. And that obviously factors, right? It's y minus xy plus x. And what this means is, first of all, that the multiplicity here is 2. So it's the degree of the first non-trivial term in the polynomial. So that means m0 of f is 2. And this would be a singular point. And there's actually two tangents, namely any linear factor of this lowest thing here. And y minus x is just this here. And y plus x is just that. So you can actually also see that sort of in the picture, right? So you would want to say that this curve has two tangents, and the definition actually does that. So there's no notation for that, as it's not unique. So that means y minus x, you can just write y minus x and y plus x are the tangents to the curve at the origin. More, namely, we have this curve that we had before even today, like y squared minus x cubed. That looks like this was that curve here. As one of the curves for our example intersection multiplicity. Here again, the lowest term is quadratic, but it's just y squared. So that means here f2 is just y squared. So again, the multiplicity at the 0 point of f is 2. It's a singular point. But there's only one tangent, right? Because there's only one linear factor just with multiplicity 2. So there might be a unique tangent even if it's not a smooth point. And that also fits nicely with the picture, because that is, I mean, if there's any line approximating this thing to the 0 point, it would be this one. Okay? Because that actually, if you compute it, it just goes in, I mean, speaking analytically, it goes in here with 0 slope. So that would be a third example. And the last one eventually is, well, a very sort of trivial one. Namely, you could even apply this to the case where there is no curve at all. So if in the real picture you take x squared plus y squared, which is a curve after all, it's a non-constant polynomial, but the 0 locus is only the origin, and because x squared plus y squared can only be 0 if we're at the origin. Then the last example, the picture here would just be this point. If we do that in the same way, then of course, like, the quadratic terms are the lowest. In fact, the only ones occurring here. So f2 would be x squared plus y squared. Again, we have the multiplicity as 2, so that means we have a singular point. And in that case, this doesn't factor over the reals. And this means we have, in fact, no tangent at all. So this might also happen. And that also makes sense geometrically. I mean, no line through the origin would be a sensible approximation of that thing. Right? That all makes sense, I guess. So yeah, that's just for those concepts that we just introduced. We can actually also other questions, by the way. It might be a nice moment then for that. Otherwise, we could just actually also rephrase our proposition about the multiplicity 1 in terms of these new words. Namely, we said that the intersection multiplicity is 1 if and only if F1 and G1 are linearly independent. And what this means in these terms is that F1 and G1 are linearly independent, first of all, means that they are non-zero. So that means the multiplicity of the point must be 1, i.e. there must be smooth points. And that they are linearly independent means that they have different zero loci. And that means exactly that the tangents differ. Right? So we can also rephrase our result about intersection multiplicity 1 and just get exactly the picture that we had after this proposition, how we could imagine this. Namely, so we'll just call this the corollary because it's the same statement as before, just with different words. And there is also a word for this sort of intersection, and this is called a transversal intersection. Actually, the name pretty much says what it means. Namely, so two curves, F and G, have UP of FD equals 1 at a point P. P and F intersect G if and only if. So first of all, I mean F1 and G1 are non-zero and are distinct as curves. So that means if and only if F and G are smooth at P. With TPF not equal to TPG, so with different tangents. And that's exactly the picture that we had before, right? Smooth curves somehow mean it does have a tangent, it does have a linear approximation. These two are actually different for the two curves. And such intersections, as I said here in the name, are called transversal. In this case, one says that the intersection of F and G at P well, that's just some names, but all pretty much for the picture like that, right? So we have two smooth curves intersecting at a point with different tangents. Now, but that's an exact statement. So we can compute all these things. So whenever we have two curves, we could figure out whether this is true or not. Yeah. So there's one thing I guess we could still do today. Oops, maybe not, but at least I'll write it down and then show it next time. So we can compute this, as I said, so the multiplicity at particular points, both the multiplicity of a point, of course, I mean, that's easy to read off, but also the multiplicity, intersection multiplicity. And however, if we want to know if the whole curve is like smooth or singular, so if there's any singular point, we would have to know the point at which we actually want to check. And there's infinitely many points, so we don't want to check infinitely many points for that, because that would not be feasible. So it's nice that there's a criterion to tell you whether the whole curve is smooth or singular, maybe whether there exists a singular point just anywhere. So say to figure out if a curve F contains a singular point, there's the following proposition. It's called the Jacobi criterion. And there's various versions. So here it's the affine one. We'll see a different one later. And that has the following. So let F be a curve. And say P is a point on F. And then there's two parts. Namely A, this P is a singular point if and only if P so P is a singular point of F if and only if we take the partial derivatives. So that's why it's called Jacobi. I mean, there's some Jacobi matrices like from analysis coming in. And there is a differentiation, like a formal differentiation for polynomials only, right? Over any field, just defined by the standard rules for differentiation. You probably maybe have seen that before. So to define derivatives for polynomials, you don't need any analysis. Actually, you just do this formally, differentiate them in the same way as you would expect. And if you evaluate this at the point P, then you get 0 for both partial derivatives. So if and only if that holds, then we have a singular point. And so there's a slight improvement of the statement, namely, if it's a smooth point, then we know it has a unique tangent. And we can actually express the tangent in terms of this point, in terms of these derivatives. So if P is a smooth point, which means that one of them at least is non-zero. Of F, and say P has the coordinates x0, y0, then the tangent P to the curve F would be these coefficients as the coefficients of the equations of the line, namely df by dx at P times x minus x0 plus df by dy P times y minus y0. So that means this criterion tells you just, first of all, whether a point is smooth or not. And if it is smooth, you can also read off the tangents, namely just from the partial derivatives. And the point that's nice about this is just that you only have to compute this partial derivative just once, right? And then you check what their common zero locus is. And then you get two equations for that, for two variables, and you can usually just solve them for the two variables. And then you know which ones are the singular points without having to go through the above procedure just for every single point. All right, that's the nice thing about this. Yeah, so I guess it would just be 1 minute left. So no, it's not true, it's 11:13. Oh, we have in the 10. Oh, then we can continue, that's great. Yeah, so we're in different slot today than usually. That's right. So we just have. Then let's go on. That's good. So that is the statement. But then we can actually see how to. And so to figure out, so what would you have to do by definition to figure out what it is, whether it's a singular point or not? We have to translate P to the origin and then check for linear terms. And I mean, that's what the definition says. Well, let's apply this definition because that's at the moment the only thing we can do. So for for p x0, y0, we just said we introduce new coordinates. So x prime would be x minus x0, y prime would be y minus y0, which means maybe we need the other way around as well. So x would be x prime plus x0, and y would be y prime plus y0. And express our polynomial f in terms of these x primes and y primes, and then check for linear terms. So, and we write f in terms of x prime and y prime. So that means we can write our f as some number a times, just single out the linear terms. Well, first of all, that would not be a constant term, right? Because the point P is supposed to lie on F. And that means that whenever you plug in the point, you would get 0 for the thing. So that means there is no constant term. So we would have an ax prime plus by prime. And then we have higher terms in x prime and y prime. And these numbers a and b can actually be expressed in terms of derivatives, right? I mean, for a polynomial, you would get a by taking the derivative with respect to x prime and then setting all the variables to 0. That's one way of doing that. So we're a would be you take df by dx prime and then plug in 0. But x prime was just x minus x0. What that means by the usual chain rule for differentiation, which holds as well, I mean, for formal polynomials, you can transfer this back to the other coordinates, and that would just be by the standard rules of differentiation, it would be the same as df by the original x, right? So there's no inner derivative because that's just shift by a constant, but we have to shift the point. So that's df by dx at the point P, just by our standard rules of differentiation. And the same, of course, for B, right? So B would be df by dy at the point P. And from that, actually, both parts follow already because we said that the curve is smooth at the point. Well, there we said it's singular. It's singular at the point if and only if there is no linear term. So the multiplicity is bigger than 1. So this means both of these numbers are 0. The numbers are just that. So that's exactly what we've written down there. And if it's a smooth point, so they are not both 0, then the tangent is by definition just that linear part. So it's a times x prime plus b times y prime. And if you plug in the values for a and b, and plug in x prime is x minus x0 and y prime is y minus y0, you get exactly that. So this is already the result. So it's very simple actually. So the nice thing is just that this exists and you can compute this for all points at the same time. Write this down. So hence what we see for A, so P is singular, the singular point by definition. If and only if A and B are equal to 0, so there's no linear term, and that's now the same by our computation as saying that both derivatives both vanish at the point. And for B, if P is smooth, then again, by definition, we have that TPF is just the linear part of that, so which we call AX prime plus BY prime, just the linear part when expressed in the new coordinates, and plugging that in gives us dF by dx at P. And x prime was x minus x0. And then plus dx by dy at P y times y0, and that shows already both parts, right? So that's quite nice, actually. Probably want to consider an example for that, namely, take again maybe the curve y squared minus x squared minus x cubed. So it's one of these standard examples, I guess. So that thing here. So we had seen already that the origin is a singular point, right? So that was the computation before, well, not computation, it's just the observation that there's no linear term in here. But with this Jacobi criterion, we can now also, in fact, check that this is the only singular point. So we want to compute all singular points. Using this Jacobi criterion. And that would be, we just compute the partial derivative with respect to x, which is minus 2x minus 3x squared. So this is supposed to be 0. And the f by dy, which is just 2y, this is also supposed to be 0. And we can solve both equations. So that obviously says y is 0. And that gives us two solutions in principle, namely the 0 point. X is 0, and another thing which is probably like minus 2/3, right? Would be the other solution of that quadratic equation. So that means in principle we get 2 points for x and y, so 2 points in the plane, but actually the other point that we get is not even on the curve if we check the equation. So if we just take the two equations from the partial derivatives, you might get solutions that do not correspond to any singularity because they are not even on the curve. And that's exactly what happens here. So our solutions are the 0, 0, and or the minus 3, 0, but this point is not even on the curve f. So that means the 0 point is actually the only singular point. And that one simple computation just shows that, right? So we will easily be able to find all the singular points. That studies sort of like the local thing of the curve. So that's we have here, right? Oh yeah. So there's one thing I forgot. So I'll just do it right now. Yeah, there were many things for today. One thing, so just afterwards in the notes, it's like a little before, is one remark just about our multiplicities here. Namely, note that our multiplicities of points are also additive. That means if we have MP of f times g, that would be MPF times MPG. Well, that's quite easy because it suffices to show that at the origin, and that would be the lowest occurring degree in f times g, and that's the lowest. Either it's just false, but in this way it's right. Right, and that would be the lowest degree term in f, and that's the lowest degree term in g. And we have an integral domain, so if we multiply the lowest degree here with the lowest degree here, we will get a non-zero lowest degree here. Right? That's just the additivity. That's very easy to see here. And what that means is, as these multiplicities are greater than 0, both of them, if the point lies on the two curves, that means that in that case where we have a product of this situation, or we have two curves both vanishing at the point, the multiplicity will always be at least 2, and hence we always have a singular point. So that might happen with different curves, f and g, or also with the same, with f squared. So if a point lies on both f and g, then in the union, sort of, an f times g, which corresponds to the union of the two, we always have a singular point. write this below that same word. So so note that, and so this means that if P lies in the intersection of two curves, then P is always, that would be then greater at least 2, so that means that P is always a singular point of F times G. And F times G is what we also wrote in our notation as F union G. So that means if we have a curve with two components and they meet at a point, then every meeting point of two components of the curve will necessarily be a singular point. That actually also holds for F equal to G, but so let me just put this here in words. So points, just points, all points of the curve where two components meet are always singular. It's probably also easy to imagine, right? So if you have a point and you have one curve which two components meeting, then of this curve, of course, the curve doesn't have a linear approximation at this point. Yeah, so that just is afterwards. Okay, but now it's just like 4 minutes, so I can just give you the next result that we want to show and then talk about it next time. And there's one last, like, sort of little bigger result, which is another sort of interpretation of intersection multiplicity 1 of a point. Not intersection multiplicity, but multiplicity 1 of a point. So this is here's another consequence of smoothness in the multiplicity 1 of the point. That's the following proposition. And called the sum of comparing ideals by intersection multiplicity. And that works as follows. So let's say we have, first of all, one curve which is smooth at a point. So let F be a curve smooth at P. And that smoothness is actually essential. And consider two other curves that don't share a common component at F. So let G, B, and H be two more curves. They don't have to be smooth, only F has to. That don't share a common component with F at P. I don't have one, so neither one has a common component. So F, G, and H might have common components, but not G and F and not H and F. So then the statement is, we can consider the ideal generated by F and G or F and H in the local ring. And I claim that the ideal generated by F and G and one of F and H in OP has this containment relation if and only if the intersection multiplicity satisfies the other way around. So if mu P of Fg is greater or equal to mu P F and H. That is the statement. And so first of all, I guess you can see one direction is sort of clear, right? Because if that is contained in that, the intersection multiplicity is defined by you take OP modulo this ideal and then take the dimension. So if you have a bigger ideal, then if you mod it out, you get a smaller dimensional vector space. So that means the direction from left to right is clear, right? And that will always hold no matter what we have as assumptions. However, the other direction is sort of interesting and nice because the thing on the right-hand side looks a lot weaker, I guess, at first, because that's just a comparison of two numbers, two intersection numbers, which we could easily compute by our algorithm that we had today. And from that, we can conclude going backwards that actually one ideal in this local ring is contained in another one. So containment of ideals is usually harder to check, right? And here it says it just reduces to the comparison of two numbers. And that we want to show and just exploit and also see geometrically what this means and how we can interpret it in terms of geometric terms next time. But then now it's really, I really have to stop now. It's 90 minutes. So if there's any no more questions, then we'll just do that next time and then continue from there. Right? Okay, so then we'll meet. So there's the first example class this week, right, on Friday, and then we'll meet again next week.